In some cases, members of a population are either harvested or stocked. If you think about fisheries or stocking lakes or that sort of thing, that might make sense. And we have a modified logistic growth model in that situation. dPdt is equal to P times the quantity of A minus B times P, plus or minus H, where if we're looking at a positive, that would be a rate of restocking, and the minus would be a rate of harvesting. And this is the situation we're considering in this first example. I know there's a lot of text on the screen. We'll take it piece by piece. If a constant number of fish H are harvested from a fishery per unit time, then a model for the population for the fishery is that dPdt is equal to P times the quantity of A minus BP minus H, right? There's that rate of harvesting. P of 0 is equal to P naught, an initial population, where A, B, and H and P naught are positive constants. So we're given values now. A is 5, B is 1, H is 4. I'm going to leave off reading now, and we're just going to tinker with this model here. dPdt is equal to P times, if A is 5 and B is 1, then we have P times the quantity of 5 minus P, and H is 4, so that gives us minus 4 there. Distributing and then factoring out a negative is going to give us P squared minus 5P plus 4, all with a negative factored out of it, right? So dPdt can be factored into the negative of P minus 1 times P minus 4. This implies that P equals 1 and 4 are critical numbers, or critical points. We can draw a two-dimensional diagram that will illustrate what solutions look like over time for various initial populations. I've given a two-dimensional plane here with a horizontal t-axis and a vertical p-axis, and we have points of interest at 1 and 4. Those are our critical points that give steady-state solutions. And suppose we have an initial population P naught that's greater than 4. Looking at dPdt equals negative P minus 1 times P minus 4, a P value, or I guess P naught value of greater than 4 is going to give us a negative derivative. So we're going to have a population that's going to decline until it levels out at 4. I'm assuming it's like 4,000 or something like that. It's probably not 4 fish. A P naught between 1 and 4 is going to grow until it again maxes out at P equals 4. And a P naught less than 1 is associated with a negative derivative. And it actually wouldn't make sense in this case to draw a curve that would go down to negative infinity because we're talking about a number of fish. And so more appropriately, what would happen is at some point, the population will just become 0. We can, of course, translate this into a phase portrait. Here's our vertical axis here. We're going to label it at, I'm going to label it at 0, and then 1, and then 4. And of course, above 4, we have an arrow pointing down. Between 1 and 4, we have an arrow pointing up to 4. And between 0 and 1, we have an arrow pointing down. It's just going to point down to 0, right? I'm not going to bother with a negative down here because that doesn't apply to populations. I mean, maybe a science fiction scenario or something. But let's go back to the instructions here. Since the differential equation is autonomous, use the phase portrait concept of section 2.1 to sketch representative solution curves corresponding to the cases P naught greater than 4, between 1 and 4, and between 0 and 1. Determine the long-term behavior of the population in each case. Well, we've got our two-dimensional picture here. If P naught is greater than 4, then it's going to decline to 4. If it's between 1 and 4, it will grow to 4. And in practical terms, if P naught is less than 1, then the population will become extinct. Next part, solve the initial value problem in part A. Initial value problem, we have P of 0 is equal to P naught. We're just going to use P naught. So the initial value problem is the differential equation together with the initial condition. So we've got dp dt is equal to p times 5 minus p minus 4, subject to p of 0 is equal to p sub 0. Well, as we just saw, dp dt it can also be expressed as the negative of p minus 1 times p minus 4, and that's a useful form because this is not a linear differential equation. Remember, we're in a lesson that's called nonlinear models. So I'm not looking for an integrating factor or anything. I got to find another way to solve this thing. And it turns out we can use the fact that it's separable. So we've got dp divided by p minus 1 times p minus 4 is equal to negative dt. And then a round of partial fraction decomposition will give us the integral of 1/3 divided by p minus 4 minus 1/3 divided by p minus 1, that whole thing times dp, is equal to the integral of negative dt. Integrating and using properties of logs gives us 1/3 of the natural log of the absolute value of p minus 4 over p minus 1 is equal to negative t plus c. Clearing the fraction 1/3, applying the exponential to both sides, and relabeling the constant on the right-hand side is going to give us p minus 4 over p minus 1 is equal to c e to the negative 3t, which will necessitate me relabeling the previous c as c1. Now the initial condition of p of 0 is equal to p sub 0 is going to give us that c is equal to p sub 0 minus 4 over p sub 0 minus 1. It's a lousy constant to have to deal with. I'm actually going to reintroduce that in a few minutes because we have some algebra to get through. We're going to solve for p. And I'll leave it to you to verify if we clear the fraction, collect our p's on one side and everything that doesn't have p on the other side, factor out and then divide to isolate p, we'll get p of t is equal to 4 minus ce to the negative 3t over 1 minus ce to the negative 3t. C is a fraction. So we've got 4 minus p naught minus 4 over p naught minus 1 e to the negative 3t divided by a denominator that looks just as bad, 1 minus p naught minus 4 over p naught minus 1 e to the negative 3t. Finally, clearing the complex fraction, we get a rather hideous looking function, but it is the solution. P of t is equal to 4 times the quantity of p naught minus 1 minus the quantity of p naught minus 4 e to the 3t. That's our lovely numerator. Our denominator is going to be p naught minus 1 minus the quantity of p naught minus 4 e to the negative 3t. I didn't write down negative 3t in the numerator there. That's the solution to our differential equation. And we find different values depending on what p naught is, and we'll pick representative values from each of the indicated intervals from earlier. Now in our instructions, we were actually asked to graph solution curves using a graphing utility, and I've done that here. I've got a slightly different form for the solution here, but we can see I've picked 5 for p naught, and what we have is a solution curve that will decline and then level out at 4. Using 3 for p naught, we have a solution that will increase and then flatten out at 4. And using 1/2 as our p naught, we get a solution curve that is going to hit 0. And that population has gone extinct. And that actually is what we have in the next set of instructions here. Use the information that we had in the previous steps to determine if the fishery population becomes extinct in finite time. That is to say, does p equal 0? And the good news is, even though p is rather cumbersome looking. The only thing that can make a fraction equal to 0 is its numerator. So using the numerator equals 0 and algebra is going to give us that t equals negative 1/3 times the natural log of the quantity of 4 times p naught minus 1 divided by p naught minus 4. It only applies for p naught between 0 and 1, but for a particular p naught, you can find out how long the population will last.